Alright guys, right now we're going to continue the video from previously and we're going to do something a little bit crazy with what we've learned. Alright, now just a quick summary, and I want to talk about one other thing really quick before we get into that kind of crazy thing. And what that is just want to talk about just what we've done. So we talked about displacement, velocity, acceleration, right? We talked about how to get the maximum displacement, velocity, acceleration from those. And so we've got our maximum displacement, which was equal to the x naught. We've got our maximum velocity, which was the x naught omega, and we got our maximum acceleration, which was negative x naught omega squared. Remember that the purpose of this was to show that the acceleration is proportional to the displacement, but negative in direction, and that's going to be important to what we're about to do. Now, one thing I do want to mention before I go any further is remember that we base these off of the initial position of our object. Okay, and that's important because these sine, cosine, sine don't necessarily have to be sine, cosine, sine. They could be cosine, sine, cosine. All right, and I want to talk about why that works just really, really quick. So remember when we did this, we were looking at the slopes, right? And we looked at the slope of the sine, and it ended up giving us a cosine graph. And we looked at the slope of the cosine graph, and it gave us a negative sine graph. Now that's important. So remember, the reason that was is because we were considering starting at equilibrium, right? And at equilibrium, remember the sine curve starts at 0, 0, and then it goes from there. It goes away from equilibrium. So if my spring is starting at equilibrium, where x equals 0, or my pendulum is at equilibrium, which would be straight in the middle of my pendulum, then in those situations, what I'm actually going to have is this sine. Now, if I don't start at that position, if I start at a slightly different position, if I start at the maximum displacement, or if I start my pendulum way over here on the left-hand side as far as it goes, that's going to change these, because now, rather than starting at the equilibrium point, I need to start with my displacement as its maximum. And so in that case, x would be equal to x naught cosine omega t. Right? Because cosine starts up at 1, which means that it's going to allow me to start when time is 0. It's going to allow me to start at my maximum displacement, because remember, x naught represents the displacement. Okay, so now that I have that, we can now find the velocity and the acceleration. And when we do that, we end up getting that velocity is equal to x naught omega sine omega t, but it's not going to be positive. Being positive is not a trait of going from displacement to velocity. What it was looking at the graph of sine gave me a positive cosine graph. What happened when we look at a positive cosine graph? It became negative sine, didn't it? When we looked at the slopes and we put down the points and all that in the previous video. So when I go from cosine to sine, it's not going to be a positive sine graph, it's going to be a negative. All right, now that's going to be important because now I'm going to go on to my last step, which is going to give me acceleration. And we'll note that when I do acceleration, I end up getting negative x naught omega squared cosine omega t. All right, now the negative stays there because when I go from sine to cosine, the sign doesn't change. We saw that here. When I went from sine to cosine in the previous video, the sign didn't change. So it's important to recognize when the sign is positive, when it's negative. Now you'll notice that in both situations, I get that the maximum is at a equals negative x naught omega squared. That's important because the maximum acceleration is always going to be opposite in direction and yet proportional to the magnitude of the maximum displacement. All right, so now that really neat kind of weird thing I was going to tell you about. Let's do it. All right, so what I want us to do is I want us to take Hooke's law and combine it with Newton's second law. All right, so you may remember Hooke's law. You did that like a long time ago. We said force was equal to negative kx, where k was the spring constant and x was the displacement. All right, and then what we said with Newton's second law is that force equals mass times acceleration. Now, what we're going to look at right now is just the point where we're at the maximum displacement. All right? So let's consider maximum displacement. If my maximum displacement, if this is maximum displacement, so that's the x naught, that means that I'm at the position where the force is at its maximum, right? We said that they're proportional, okay? So the magnitude, anyway, would be at its maximum. Now, if I look at that same position, the maximum force for F, what does that mean about the acceleration? Well, it means that it's at its maximum value. Okay, so we're going to look at the maximum value of the acceleration. So if we put those together, because they're now equal, because I'm looking at the position of the maximum force for both of them, what do I end up with? Well, I end up with this. I got negative kx naught is equal to mass times the acceleration at the maximum point. Now, what does that mean? Nothing yet. We're not there yet. We're going to get there. So what we're going to do is we're going to say, well, here is the acceleration maximum, which we already found in terms of the displacement. The maximum displacement was, maximum acceleration was the negative maximum displacement times omega squared. So we're going to put that in for the acceleration. All right? So we got negative k x naught equals the mass times the maximum acceleration, which we just stated was negative maximum displacement times omega squared. Now, you may remember that in the last video we also talked about omega, didn't we? Because omega is kind of a weird thing in our brain, and sometimes we can figure it out, sometimes we can't. But it is important because it works mathematically with all these other cool things. So, we also talked about omega, and what we said was that omega is equal to 2 pi over t. Or you may recognize it as t equals 2 pi over omega. It really doesn't matter which one you do. They're the same thing, right? This one I multiply by t and divide by omega, and I get this one down here. So either way, same thing. But the one I'm going to use right now is this one up here because I can substitute the omega straight in. Now, recognizing in the IB booklet, I believe this is the one that they give you, so just recognize that they're interchangeable more or less, and that you can get one from the other if necessary. All right, so I'm going to go ahead and put in for omega. I'm also going to recognize in the same process, because I'm going to be efficient here, that both sides have displacement and they both have a negative. So I'm going to cross those out. Now this should make sense. Remember back in the day, like 2 weeks ago, when we first started talking about simple harmonic motion, we were talking about the fact that if I extended the spring a little bit further, it wasn't going to change the period. We even tested it out. Remember, some of you believed me, some of you didn't. We tested it out with the motion detector. I stretched a little bit further, like 20 extra centimeters, like twice as far or something, and it still ended up giving us the same period as it oscillated up and down. All right, so we already knew that displacement didn't matter, and this is where mathematically we can see that it doesn't matter, because it affects both the acceleration and it also affects this force on this side, and so therefore it cancels out on both sides. It doesn't really matter. All right, so what I'm left with here is k equals m times omega, which is 2 pi over t squared. What I'm going to do is I'm going to solve for t, because that's just kind of cool. So we're going to go ahead and solve for t. By doing that, we're going to square both sides. So I'm going to have k equals mass times 2 pi. We're just going to go 2 pi squared over t squared. Then I'm going to multiply both sides by t squared, divide both sides by k. I'm going to put the k under the m instead of under the 2 squared. It doesn't really matter, but it's going to look better that way. So t squared equals m over k times 2 pi squared, and then I'm going to square root both sides because I can, and because if you do the same thing to both sides, it doesn't really matter. So I go t equals square root of m over k, and of course the square root of 2 pi squared is just 2 pi. Now the way that you'll usually see this written isn't like this, it'll just be like this. It'll look like t equals 2 pi square root of m over k. And that, my friends, is the period of a spring. Okay? You can see that it depends on the mass. It depends on the spring constant. That's not spring constant, that's 2 pi. That's the spring constant right there. And so it depends on those two things. You can kind of figure out that if the string is stiffer or if it's more stretchy, that might affect the period. The mass of the object obviously is going to stretch it because that's going to affect your mass times acceleration here, but it doesn't affect the other side. So therefore, acceleration is going, that will affect your acceleration, and therefore your period. All right, so anyway, there you go. I think that's kind of cool, kind of weird that we can put those two things together and get something actually kind of neat and significant, but there you go. You now know how to get the period of a spring.